Roy Trebline, BioBites. Today we're going to talk about the properties of water, which was an essay one year for the AP exam. They asked what are the, pick 3 properties of water and explain the biological significance. That's what I'm going to do for you right now. These little mouse-like structures, like my wife called them, are actual water molecules. The ears are representing the hydrogen, and the big head is representing the oxygen. As you can well imagine, the oxygen is much more stronger than the hydrogen. Much more stronger. Much stronger than the hydrogen. And so there's much more there's much more electronegative pull. The oxygen hangs on to those electrons that they're sharing. It's covalent bonding, but the oxygen hangs on to those electrons much more than it does to the hydrogen. So the hydrogen are slightly positively charged, and the oxygen is going to have a slightly negative charge. And because there's 2 orbitals in this oxygen, there's actually 2 negative charges. So I want you to treat those water molecules like my hands are the hydrogen and my feet are the oxygen. And so technically, water molecules can attach to 4 other water molecules just by something called hydrogen bonds. Just like dating, molecules, opposites attract. Because those water molecules have polarity, charges, opposite charges of the 2 water molecules will attach to each other. Right, Mrs. Trebline? Opposites attract.
Yes.
These green lines are representing those hydrogen bonds. And I drew them as dotted lines because hydrogen bonds are extremely weak. But if you've ever done a belly flop in the pool, you might say, hey, Mr. T, those hydrogen bonds in large numbers are strong. Water molecules attach and deattaches to other water molecules continuously. And all of those hydrogen bonds together gives water something called adhesion and cohesion properties. Adhesion means water sticks to other substances, and cohesion means it sticks to itself. My memory cue for that is cohesive tape would be a ripoff. You'd never be able to get it off the roll, right? It sticks to itself. You want to buy adhesive tape. Water has both properties. It sticks to itself and it sticks to other molecules. If we look at this here, plants going up what we call the xylem. This Trelline's going to get a close-up here. I don't know if you can see it, but the food coloring took it in very well. This end of a celery, you can see where all the xylem are. Those are the vessels inside plants that carry water through the plant, from the roots all the way up to the leaves. 400-foot redwood, no biggie. Water goes right up through those roots and through those leaves by this property of adhesion and cohesion. Now think about this. Here's these water molecules stuck to each other, making a long chain, pulling each other up through those leaves, right? And at the same time, it's sticking to the sides of the xylem. It's literally walking up the walls of that xylem because it has the properties of adhesion, sticks to the xylem, and cohesion, sticking to itself. If there's ever a break in those bonds, there'll be a break in that water. The water can no longer be pulled out those 400-foot trees. It's adhesion and cohesion that makes water go from the roots all the way out those leaves. Water has a high specific heat. By definition, what that means is it has 1 calorie per gram per degree Celsius to move that temperature. In other words, as you well know, water takes a long time to boil. You go to the beach on a hot June day, it's 100 degrees out. You go on the sand, ooh, ow. Sand is really hot, very low specific heat. It changes temperature very quickly. You get to Lake Michigan, that Lake Michigan has a high specific heat. The water does not change temperature very easily. You jump in that water and you freeze. You might want to wait till August to jump in Lake Michigan. It takes a long time to break those hydrogen bonds. High specific heat is a property of water. It all goes back to those hydrogen bonds. I always joke with my students on this test, if it talks about water, the answer is hydrogen bonds, right? It's that polarity between those water molecules that makes it happen. Water going from heat to a liquid, from a liquid to a gas is called heat evaporization. Heat evaporization is also a great property of water. On a hot day, sweat comes off my skin and it cools me off. The faster moving water molecules leave my skin, giving my overall skin a cooler temperature. I usually ask people, who's the fastest in the room? If you leave school, you go to a different school, what's going to happen to the average speed of our school? If the fastest runner leaves, it's going to become lower. When the faster moving water molecules go from liquid to gas, the overall effect is cooler. Now, a little less appetizing, what if you wet your pants? At first, it's warm, huh? Ooh, right? But wait around a couple of minutes and it gets very cold. The faster moving urine molecules leave my skin, the overall effect is a cooling effect. Kenzie, panting her tongue, that's my dog. Faster moving water molecules leave her tongue, it cools her off, right? Heat evaporization is from liquid to gas, and it takes a lot of energy to do that. But the faster moving water molecules leave, overall effect is cooler. Now, versatile solvent.
I missed.
You'll notice that I'm using a cotton towel that my wife just threw water at me. This towel is solvent in water. Now stay with me. It's large molecules, but it likes water. It attracts water. When I wipe my face, the water goes from my skin to the towel. We're going to call this towel hydrophilic. Yeah? Universal solvents will dissolve things. Now, sorry, not universal, but versatile. Take a look at this sugar, right? Sugar is hydrophilic. I dump it in the water. You've done this, and now I've made Kool-Aid. The polar charges of the water molecules attach to the polar molecules of the sugar. Now, is it a universal solvent? I said that earlier, and that is wrong, right? Take a close-up look at this oil and water mixture, Mrs. Treveline. This is our Italian salad dressing. You'll notice that the water and oil do not mix. They create a barrier in the middle. Just like our cell membrane is made of lipids. And those two substances do not mix. Well, they can mix, but they'll soon go apart again, right? So we don't want a universal solvent. We want a versatile solvent. We want something that's going to dissolve most things, but not lipids. And that's why our cell membranes are made of lipids. We don't want our cell membranes to dissolve. Last two properties of water, how are we doing on time, Mr. Treveline? 8 minutes. Is that water is less dense as a solid as it is a liquid, right? We take this for granted, but here on Earth, this is a miracle. Look at the solid particles on the top and the liquid below. Tell me what other substance where the solid is less dense than the liquid, right? We've been making ice water for years. We know that ice floats. But if you think about that, there's very few substances where the property as a solid is less dense than it is as a liquid. But boy, isn't that nice. Let's go back to Lake Michigan. Here's my little fishies below, right? Since the lake freezes from the top down, my fish can survive in very cold water. Hence ice fishing, huh? I can stick my pole still through there and get to the fish. The fish are in here and they're being insulated by the ice above. Hydrogen bonds, when they form, release heat. It insulates the water below. Water as a solid forms a crystalline lattice. I froze this beaker of water. I don't know if you can see it, but it came up above the water. Maybe you've had this mistake where you put a bottle of something in the freezer and the bottle explodes because the ice expands. It forms these crystalline lattice and it goes back to these hydrogen bonds. Up until about 4 degrees Celsius, the water can slide past each other. But at 0 degrees Celsius, what water freezes at, all these crystalline lattice are going to lock into place. And there's actually more space between the molecules of water, not less. Think about that for a minute. Liquid water is more dense than solid. Last, my wife's telling me I got to be done. My last trait, she must have to go watch a movie. My last trait here is water is pH is 7, right? We take that for granted, but water lasts in our body. All of our proteins, we'll talk about these eventually, that shape of the protein, that tertiary structure is going to remain the same shape because pH of water is 7. Anything below 7 is going to be acidic. We're going to break those proteins apart. Anything higher than 7, relatively speaking, is going to break those proteins apart. We are mostly water, 70% water, because we want to be neutral. We want equal number of hydrogen and hydroxide ions. We don't want to be too many of either way. This is Roy Trevelyan. It's Biology Bites. Thanks for watching.
Bye.